In this video, we will explain the notion of gates and we go through some linear algebra. Let me remind you our interpretation for a qubit. We have to use two disks. We label this disk state 0, this disk state 1, and for a qubit, we have a segment that starts from the center with length R1 and another segment that starts from the center with length R2 with R1 squared plus R2 squared equal 1. And in order to describe a qubit, we need two vectors. Sorry, we need one vector with two complex numbers. We will denoting this as C1 0 plus C2 1. But then we need an element in C2. For elements in C2, we may say we can take C1, C2, the vector C1 or C2, or the column vector C1, C2. We're going to see that it is very convenient to use for this qubit the column vector. And we're going to denote this qubit. We're going to give it a notation like this, with this arrow pointing to the right, and we're going to call it a ket, right? A ket would be this, and it's going to be represented by the column vector C1, C2. And given a ket, its bra, the bra, is going to be given by the row vector C1 conjugate and C2 conjugate. Let's do an example. If we have this ket to be equal to the square root of 3 over 2 state 0 minus 1/2 I over 2 state 1, and we have this ket to be equal to let's say 1 over the square root of 2 0 plus I over the square root of 2 1. Then we have that this is this column vector, the square root of 3 over 2 negative I over 2, and this is also equal to the column vector 1 over the square root of 2 and I over the square root of 2. And then we can do, for example, the product of this bra. Remember, this bra is going to be, this is a 2 by 1 matrix. It can be viewed as a 2 by 1 matrix. Then this is going to be a 1 by 2 matrix. And we can multiply this matrix with this ket, which is C, and this is a 2 by 1 matrix. Let's see this product. This product is going to be, this is the ket. Its bra is going to be the row vector that we get by conjugating this. Then here we have a square root of 3 over 2, comma, I over 2. The conjugate of negative I over 2 is just I over 2 times this column vector, 1 over the square root of 2, I over the square root of 2. And then what do we get? We get this times this is a square root of 3 over 2 the square root of 2. I times I is negative 1 minus 1 over 2 the square root of 2. In this case it's a constant, but in general we get a complex number. Usually this notation, when we are doing this product, we're going to change these two parallel vertical lines into just one, and we're going to denote this like this, and we're going to call this the product of a bra and a ket. We're going to call it a bra-ket between the two vectors. Let me remind you the definition of an inner product on Cn. If we have Cn, if we have a collection of vectors, let's say C1, Cn, and W1, Wn. Then the dot product between C, if you call this C, and this W, the Hermitian inner product between C and W is going to be C1 conjugate, the conjugate of this times W1, plus C2 conjugate times W2, plus Cn conjugate times Wn. The inner product provides a notion of distance and angle. For example, we can check that if we do the inner product of C with C, we essentially get the length square of C, and somehow the information about the angle between C and W is here in this inner product. If we have two vectors, let's say I have this vector phi, which is, let's say that we have this like C1, C2, right? This is a ket, and we have another ket W1, W2. Then what would be the bracket between these two? The bracket between these two is going to be, the bra of this is going to be C1 conjugate, C2 conjugate, times W1, W2, and this is just C1 conjugate, W1 plus C2 conjugate, W2, and it is exactly the dot product between the two kets. Then we think about this column vector and this column vector, and we think about the inner product. Essentially, we need to do the bracket between the two. When we think about a quantum computer can do some things on qubits. What can a quantum computer do on a system of qubits? And the answer is that a quantum computer can change a qubit into another by a linear isometry. But what are the linear isometries in Cn? Let me just say linear isometries in Cn are given by unitary matrices. And the definition is that an n by n unitary matrix, let's say U equal to A11, A12, A1n, AN1, AN2, ANN is a unitary matrix is if his Hermitian adjoint, which is the matrix A11 conjugate, A12 conjugate, A1n conjugate, AN1 conjugate, ANN conjugate. We do the transpose and we do the conjugate, and this is denoted by U dagger. This is this symbol here. And a matrix U is a unitary matrix if we have that U times U dagger is equal to the identity. We can check that if this is true, then U dagger times U is also equal to the identity matrix 1, 0, 0, 0, and 0, 0, 1. We have, this is the property for a matrix to be a unitary matrix, this condition here. Then if we have a quantum computer, we have an action given by a unitary matrix, then this is what is called a gate. Then a gate is something in the quantum computer that changes qubits by a unitary matrix. Let's think about just one qubit. If we have one qubit, then we have something like C1, 0 plus C2, 1. And let's suppose that we have a gate. A gate will look like A, B, C, D. And then what is the action of this gate with this to this ket? Then we get that this is A times C1, C2, and then we get AC1 plus BC2, and here we get CC1 plus DC2, and then this gate, which is a unitary matrix, will change this ket into this ket. A equal to AC1 plus BC2 state 0 plus CC1 plus DC2 state 1. Notice that the condition for this matrix is that it is a unitary matrix. Let me just redo this for this example, A, B, C, D. If it is a unitary matrix, it means that the product with its Hermitian adjoint, which is A conjugate, B conjugate, C conjugate, D conjugate, and this is equal to A conjugate plus B conjugate. Here we have A, C conjugate plus B, D conjugate. Here we have C, A conjugate plus D, B conjugate. And the last entry here is C conjugate plus D conjugate. We want this to be the matrix 1, 0, 0, 1. But that means that this, which is the length of this row, must be 1, and this, which is the inner product of these two rows, must be 0. That means that a matrix, a 2 by 2 matrix, is a unitary matrix if each row has length 1 and the rows are perpendicular to each other. We can check that also. If we have a unitary matrix, then the columns, they must have length 1 and they must be perpendicular to each other. Now let's try to solve the following problem. Let's suppose that we have a system of 2 qubits. We have qubit 1 and qubit 2. And we have a matrix A. Suppose that we have the matrix A equal to A11, A12, A21, A22, a unitary matrix acting on qubit 1. And we have a matrix B, same thing, B11, B12, B21, B22, and this matrix is acting on qubit 2. Then, since we have these two gates acting on qubit 1 and qubit 2, and we have the whole system, then for the whole system, we need to describe a matrix which is a 4 by 4, because remember, for a 2 qubit, we have an element in 2 qubits are represented by elements in C4, and a gate in C4 is given by a 4 by 4 unitary matrix. But what is this 4 by 4 unitary matrix? What is this gate for 2 qubits? Let's do that. The way to do it is, first we're going to think about a horizontal line, and this horizontal line is going to represent qubit 1, the lowest one, and then we increase. Qubit 2 is going to be represented by the second horizontal line, and we have a qubit 3 will be the third horizontal line. And here we're going to do the matrix A, and here we're going to do the matrix B. And we want to find a unitary matrix U, which is a 4 by 4. And this unitary matrix is representing a transformation from C4 to C4. But in order to describe a matrix of a transformation, we need to know its action on this vector and this vector, and the vector is 3 and the vector is 4. But remember that we have done the identification that this vector goes with this qubit, and this one goes with this state, and this one will go with this state, and this one will go with this state. Remember that we are using like binary numbers. This is number 0 in binary numbers, this is number 1 in binary numbers, number 3 in binary numbers, and this is number 3 in binary numbers. And our interpretation says that when we have something like ij, that means that we have this state for qubit 1, and we have this state for qubit 2. And we have, this is the interpretation. Then we need to know what is the action of this transformation on E1 on this state, but this state is qubit 1 is a state 0 and qubit 2 is a state 0 as well. But then if we think about this, and on the other hand, this goes with 1, 0, right? This vector, then what is the product of A on this vector? When we do this, we get A11 state 0 plus A21 state 1. And likewise, we get B11 state 0 plus B21 state 1. And what 2 qubit is this? We need to do the tensor product, right? And to do the tensor product, we get B11 A11 0 0 plus B11 A21 0 1 plus B21 A11 1 0 plus B21 A21 1 1. And what column is this? That is that this one goes with vector E1, this one goes with vector E2, this one goes with vector E3, and this one goes with vector E4. That means that the first column of our matrix U, the first column is going to be B11 A11, B11 A21, B21 A11, and B21 A21, right? This is E1. This is going to be the first column of our matrix U. What is going to be the second column? For the second column, we need to see the action on E2, but E2 is given by this state 0 1, and this state means that qubit 1 is here in this state 1, and qubit 2 is a state 0. Remember that we have that this interpretation is this is the vector 1 0 and this is the vector 0 1. Okay, then what changes? Here we have state, this state, that means we have this vector, and when we see the action, this gate acting on this state, we get A12 and A22. And then what changes? Here, instead of this, is going to be A12, A22, B, this is a 1 2, and this is a B, this is an A22. And then the second column of this matrix is going to be B11 A12, B11 A22, B21 A12, and B21 A22. And when you do the third column and the fourth column, you will see that you will end up with this, a matrix that goes like this. This matrix has like 4 blocks, 4 2x2 blocks, and the first block, the first 2x2 block is going to be a B11, the matrix A. This block here is going to be a B21 the matrix A, and if you do this one, you will be getting B12 matrix A and B22 matrix A. What we have done is what is called the tensor product of the matrix A and B. A tensor product with B. If you are using the software Mathematica to do this tensor product, you will be using something that is called Kronecker product between B and A. Okay, let's see a particular example of a gate acting on two qubits. Remember, we need to have a unitary matrix, but let's think about this unitary matrix. Let's call it U equal to 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 negative 1. This is a unitary matrix, and then this unitary matrix, for example, will take this ket, these two qubit, let's say C1 0 0 plus C2 0 1 plus C3 1 0 plus C4 1 1. Remember that this is identified with this column vector C1, C2, C3, C4, and we will see that this unitary matrix will take this ket into the ket C1 0 0 plus C2 0 1 plus C3 1 0 plus C4 1 1. This is an example, and it's a very well-known example. It's called the CC gate, and something that it can be shown about this example is that this gate is not it doesn't come from a tensor product of two, let's say, it cannot be written as a tensor product of two 2x2 matrices. This is a 2x2 unitary matrix. This is a 2x2 unitary matrix. If you consider every possible product of two unitary matrices, you will never get this gate. By the way, when you have a 2x2 unitary matrix, if this is a 2x2 unitary matrix, then we call this a local gate. If we have a 4x4 unitary matrix, and this matrix U has this form, is the tensor product of two. It comes from like two. We were using this. It comes from a local gate on qubit 1 and a local gate on qubit 2, then this is called a local gate. A local gate on 2 qubits. And when something doesn't look like this, it's called a non-local gate. Non-local gate, then it's a unitary matrix, if we are thinking about 2 qubits, that is not a tensor product of two 2x2 unitary matrices. Then this is an example of a non-local gate. We can also use the horizontal lines to describe this local gate. Usually the notation is that we're going to use this local gate is going to be described by this symbol. And this symbol is going to say that if you have a state here and a state here, it's going to do nothing unless these two states are 1 and 1. And when you have 1 and 1, then you get like negative 1, 1. You can write this like this, negative here, you can put the negative here, or you can just put it here in the middle, but it's just going to change the sign. We see how, for example, this is saying that the vector E4 goes to negative E4, and this is represented here in this column. Remember that if you have like 0, 0, this is the vector E1, but the interpretation is that these two dots connected with a segment, it does nothing unless it's 1, 1. That means that it keeps it the same, and then E1 will go to E1, and that's this column here, and so on. Then this is the notation for the CC gate. There is another notation that is very well known, and is this one. Let's suppose there is a dot here and a plus here. And this means that this is called a control knot, or a C knot gate. And it means that when the state here is 0, nothing happens to this. And if you have this will go just to the same, because the control gate is at 0. When the control gate is at 0, nothing happens. But now what's happening if the control gate is at 1? If the control gate is in the state 1, then if you have a 0 here, you will change it to the 1. And if you have a 1, you will change it to a 0. You do the knot of this state if the control gate is at 1. Let's find out what is the matrix of this control knot. We need to know what is the effect. Let's call this matrix the matrix U. Then we need to know what is U of E1, but remember that E1 is this state, and then we have here this state, right? And this state will go to the same. That means that we have, and this is the vector E1. Now, what is U of E2? E2 is this state. That means that qubit 1 is at 1, and qubit 2 is at 0. Then, since the control qubit is at 0, then nothing happens. Then we end up with the same. Now let's see U of E3. E3 is this qubit, is this state. That means that qubit 1 is a state 0, and qubit 2 is a state 1. And here, when the control qubit is at 1, you just leave it at 1, but then the other qubit is going to change into 1. It's going to do the knot, right? Knot of 0 is 1. Then, and this is E3, but the output here is E4. Then we have the 0, 0, 0, 1. And finally, if we compute the action of U4, this E4 is 1, 1. Then we need to know where, here we have E4, which is 1, 1. And then it will go to the control qubit is at 1. That means that it's going to change this 1 into 0. And this is E3. We have 0, 0, 1, 0. Then this is a C knot. We also have another C knot like this. We can have the control here and the C knot here. can have this gate too. Let's review some important local gates for just qubits. Then we are talking about 2 by 2 unitary matrix. We have this matrix H, which is the matrix 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, negative 1 over the square root of 2. We have this matrix H, which is called the Hadamard gate. And then we have, for every theta, we have Rx of theta, which is cosine of theta over 2, negative I sine of theta over 2, negative I sine of theta over 2, cosine of theta over 2. We can check that this is a 2 by 2 unitary matrix, and therefore this defines a gate. And Ry of theta equal to cosine of theta over 2, negative sine of theta over 2, sine of theta over 2, cosine of theta over 2. And also again, this is a unitary matrix. And the last gate that I want to write down here is Rc of theta, and this is e to the negative I theta over 2, 0, 0, e to the I theta over 2. The reason for this notation R, it comes from rotation, and is that when we think about the interpretation for a qubit using the box sphere, then we have that, if we think about the box, remember that we have these two states here. If this is the x-axis, the y-axis, and the z-axis, when you apply a rotation x of theta, essentially you are doing, and you have a qubit here, then you are doing a rotation around this x-axis. This Ry is going to be a rotation along this y-axis, and this Rc is going to be a rotation of that qubit into the z-axis. And another important gate is just the 1, 0, 0, 0, I. This is a unitary matrix. And we have some examples of some local gates on qubits. Let's just state with this one, and let's practice the circuit notation. What do we get if we apply, what gate do we get if we apply the H, the Hadamard gate, and then we do a CC, and then the Hadamard gate, and then the Hadamard gate, right? We are acting on two qubits. Let's say this is qubit 1 and qubit 2. And then we are supposed to describe a 4 by 4 unitary matrix. What 4 by 4 unitary matrix is this? Then we need to find out the action on E1. Remember, E1 is just this, which means we need to find out what is the action on this qubit. Before doing that, let me remind you that if we do H of this state, what do we get? We get H of the vector 1, 0, and then we get 1 over the square root of 2, 0, plus 1 over the square root of 2, 0. And what is H on this state? This is H of 0, 1, and this is 1 over the square root of 2, 0 minus 1 over the square root of 2, 1. Another important property is easy to check that if you do h squared, which is h times h, you get the identity matrix. That means that if I do h of the state 0, I get the state 0, and if I do h of the state 1, I get the state 1. Okay, then we need to keep track of what happened when we have this. This is we're trying to find out the first column of the matrix 4x4 that is represented by this circuit. In order to do that, I'm going to keep track here. When it moved here, let's call this stage 1. And when it moves from here to, when it goes through the CC, remember this is the CC gate, this is a stage 2, and then the final stage. Then we start here. Then when we are at stage 1, let's try here. At stage 1, this becomes, nothing happens to this state, and this state becomes 1 over the square root of 2, 0, plus 1 over the square root of 2, 1, which is just h of 0. What 2 qubit is this? We do the tensor product of these two, and what do we get? We get 1 over the square root of 2, 0, 0, plus 1 over the square root of 2, 0, 1. This is stage 1. Now when we move to stage 2, stage 2 is applying the CC, but we know that the CC does nothing to this qubit, and it does nothing to this qubit. That means that it stays the same, right? Then at stage 2, we have the same. And then what happens when I apply H again? Then I will get, this one will go to state 0, and this one will go to h of 0, which is just 0. That means that here we get 0, 0, and that means that the first column of our matrix, 4x4 matrix, is just 1, 0, 0, 0. E1 goes back to E1. Let's see the action on E2. E2 is 0, 1. That means that qubit 1 is in a state 1. Same thing here. At stage 1, we are at h of this one, this vector here is just the vector 0, 1, and h of 1 is this qubit with a minus. H of 1 is this qubit with a minus, right? And then we get, when we find the 2 qubit, we do the tensor product, and then we get this. And what happened when we move from a stage 1 to a stage 2? We notice that nothing happens because the CC does nothing to this qubit, and it does nothing to this qubit. That means that we will end up at stage 2 with the same qubit. And when we move to the final stage, we need to apply H to the qubit 1. When we do that, we apply here H of 1, and we end up with 1. It means that we end up with just 1. That means that the second column is 0, 1, 0, 0. What would be the third column? For the third column, we need to apply the transformation to E3, but E3 is identified with this qubit, 2 qubit. It means that qubit 1 is at stage 0, and qubit 2 is at stage 1. Then let me raise this to over. Then after stage 1, qubit 2 is going to stay the same, right? And qubit 1 is going to change into h of 0. But h of 0 is 1 over the square root of 2, 0 plus 1 over the square root of 2, 1. And what is this? This is the tensor product. To find the 2 qubit, we have 1 over the square root of 2, 1, 0 plus 1 over the square root of 2, 1, 1. When we move to a stage 2, we need to apply the CC, but the CC, it does nothing to this qubit, and it changes this by a negative. That means that at stage 2, we have 1 over the square root of 2, 1, 0, minus 1 over the square root of 2, 1, 1. I can write it like the tensor product of 1, tensor product with 1 over a square root of 2, 0, minus 1 over the square root of 2, 1. Remember, this part here is h of 1. Then this is just 1 tensor product with h of 1. But then when we move from, this is a stage 2, when we move to the final stage, we need to apply h to qubit 1. Then this one stays the same, and this one changes to h of 1, which is just the state 1, 1. Then this is 1, 1, which is just the vector e sub 4. And here we have 0, 0, 0, 1. Finally, let's do the last one. Let me erase all of this. For the last one, we need to find out what is the action on E4. But E4 is given by this combination of these two states. Then at stage 1, we have here 1 on top, and on the bottom we have h of 1, which is 1 over the square root of 2, 0, minus 1 over the square root of 2, 1. Then when we do the tensor product, we get this state. 1 over the square root of 2, 1, 0, minus 1 over the square root of 2, 1, 1. Then at stage 2, we need to apply the CC. And then this changes into 1 over the square root of 2, 1, 0. This stays the same, and this one changes the sign. It will be plus 1 over the square root of 2, 1, 1. And I can write this as a state 1 tensor product with 1 over the square root of 2, 0, plus 1 over the square root of 2, 1, which is just h of 0. And then when I move to the final stage, this will be changing into 1, and this will be changing into h. I have to apply the other h of 0. Sorry. Yes. And then I will be getting 1, 0. 1, 0, which is the vector e sub 3. And we have seen this before. Remember, this is the circuit that comes with this CNAT. Then with this example, we have shown that this circuit, the gate, this gate, which I'm drawing like H, a CC, and an H, that this gate is equal to this gate. The matrix represented by this gate is the same as the matrix represented by this gate. Likewise, we can do, we can check that if we have this circuit, this will give you just the other CNAT. And we have this. I think that I would like to stop here for this video.